Okay, for now, as an intro, don't look at your notes first. I'm just going to give a quick introduction of what is recurrence relations. We do this chapter 16 after AP and GP for a simple reason that it's actually related. It also makes use of some prior knowledge of AP and GP. Let me use a very simple example. 1, 3, 5, 7, 9, dot, dot, dot. This is an arithmetic progression, is an AP. Can I safely say that UN equals to 2n minus 1? Correct? 2n minus 1. How do I get 2n minus 1? Actually, you should know by now, UN for an AP is A plus n minus 1d. Now, if my A is equals to 1, my D is equals to 2, you will get 2n minus 1. No problem. Which means if I tell you if I want to find what is U10, what is the 10th term, you can tell me is 19. Correct? Yes? Easy. Now, I am now expressing UN, that means the nth term, in terms of n. Okay? In terms of n. That means this expression is the one that I'm interested in. This UN, this one is in terms of n. Now, can I define this series in another way? What do I mean? Can I say this? The same series, can I say now that UN plus 1 equals to UN plus 2 and U1 equals to 1? What do I mean by this? That means all I'm saying is the next term is the previous term plus 2. That means all I'm saying is U2, this one, U2, is equals to U1 plus 2. Is it the same? And U3 is equals to U2 plus 2. And I also define the first term, U1 equals to 1. With the combination of these two, I can define the same series. Does it make sense? They are the same. Whether I define it like this, in terms of n, or like this, they are the same. This way, the right-hand side of expressing a series, okay, is what we're going to discuss in this chapter. Hold on a second. This is what we call recurrence relation. That means the next term is expressed in terms of the previous term. Hold on a second. Yes, that's essentially the essence of actually page 1. Or what is that page? Page 46, is it? Page 46? Yeah. That's all it is. Okay? Now, okay, I just gotta go on and find and give another example just to make it complete. If you think about it, if I have 1, 2, 4, 8, 16, 32, and 1. This obviously is a GP. Correct? And I can say that UN is equals to 2 to the power of n minus 1. Correct? Or I can define it in another way by saying UN plus 1 equals to 2 UN and U1 equals to 1. I can define it like that, or I can define it like that. They mean the same thing. The one highlighted in yellow is one way of defining, the one highlighted in green is another way of defining. Follow the one. It's essentially the same. Okay, that's all we are interested in looking at. So actually, first you must really understand this basic idea of expressing the next term in terms of the previous term. Okay? Get it? Okay, then if you get it, then we go on to the notes. Then you can actually read some of the things on your own. And for a GP with common ratio R, now, just now we talked about the common ratio, right? 1, 2, 4, 8, 16, right? Now, can we safely then say this thing? The next term divided by the previous term is actually equals to the common ratio. And of course, if you make UN plus 1 the subject, you can quite easily write this is UN times up. Can? Follow? So I'm not going to go through the wordy part of page 46, but the basic idea is what I've written just now. Is that alright? Can? Okay? So idea is very simple, but when it comes to the problem, it may be a bit complicated. So please stay with me. Alright? So let's do definition first. A recurrence relation is an equation that relates some term in the sequence to some preceding term. But for the purpose of this syllabus, we will only take a look at of this form. Each term is dependent only on the previous term. Only on the previous term. Because there are a lot of recurrence relation. It can depend on 2 terms before. It can depend on 3 terms before. Or it can depend on the combination of the previous term and the previous 3 terms. But for the purpose of this syllabus, we are only interested in looking at this kind of form, where it is only dependent on the previous term. Okay? We contrast the recurrence relation with an explicit formula. Explicit formula is something like this. That means it's expressed in terms of n only. It's explicit. That means I give you 10, you know what's the 10th term. But recurrence relation, the 10th term will depend on the 9th term. So you must know the 9th term before knowing the 10th term. Follow me so far. Can? Questions? Sorry? All good? Okay. Now, let's take a look at example 1. Example 1, you are given a recurrence relation. Let's look here. You are given this. And can I say that a recurrence relation is never complete without the first term? Right? It's never complete without the first term. Let's use just now, the example just now. If I only give you this, it's not complete. If I only give you this, it's not complete. This series, this one, can easily be 10, 12, 14, 16, ... Correct? Can easily be that. I must write what is U1 equals to 1. Only then is it complete. Only then can we reject this one. We must always give the first term. So, example 1, obviously, first term is given, and then the UN plus 1 in terms of UN. Okay? Now, the question asks us to find UN in terms of n, which means the question asks us to find an explicit formula. Correct? The question asks us to find an explicit formula. Now, let's see if we can find a pattern, okay? Example 1, let's see if we can find a pattern. Okay. U1 is this 3. Alternatively, I can write it as 6 over 2. U2, you substitute n equals to 1 here. I get 1 plus 1 over 1 plus 2 times U1. You get 2 over 3 times 3, you get 6 over 3. And then and on, you realize that there is some kind of pattern here. The numerator is always 6, 6, 6, 6, 6. And then the denominator is successive like that. 2, 3, 4, 5, 6. Now, by spotting pattern, you therefore say that You therefore say that, oh, okay, I know. Now un is 6. The numerator must always be 6. The denominator is just n plus 1. Can I warn all of us that by writing that, it is only just a conjecture? That means we have not shown that this formula does, the question here is, does this work for n equals to 6? We have not shown that it has worked for n equals to 6. We have shown that it has worked for n equals to 1, 2, 3, 4, 5. But we have not comprehensively shown that it has worked. It will work for n equals to 6. Correct? Not comprehensive. Just a conjecture. That means a guess. Conjecture means guess. But we have not comprehensively shown it. Now, what is a better way? What is a better way? A better way will be we will start off with the recurrence relation. That means this is given. Will never be wrong. Will never be wrong. This is given. Will never be wrong. Yeah? Okay. Then what is un minus 1? You repeat the recurrence relation on un minus 1. That means you use the recurrence relation to say un minus 1 is actually equals to n minus 1 over n un minus 2. This is using recurrence relation as well. It's just that I replace the n with n minus 1. Follow so far? Follow so far? Do you get this? Yes, do you know how to get this? Because earlier in, maybe I should. In the question, it says this, right? Question says n plus 1 over n plus 2 un. Correct? The question says that. This is given in the question. Oh, sorry. So I explained the highlighted yellow first. I explained the highlighted part in yellow first. If un plus 1 equals to n plus 1 over n plus 2 un, what is un? I need to replace the n with n minus 1, replace the n with n minus 1, replace the n with n minus 1. I will get this part in yellow. So far, so good. Okay? Now, I repeat the recurrence again. Alright, again, what is un? What is this part in un minus 1? So I replace the n with n minus 2. N minus 2, n minus 2, I will get this expression. Follow? Wow, you all look a bit lost. I'm a bit scared. Okay? Are we okay? Yes, Okay. Now, too bad a lot of things are printed for you, so I really cannot see whether you are following me or not. Okay, let's try one more time. Now, so I can replace the un minus 1 with this. Now, you realize that there is some kind of pattern here. I can cancel this away, cancel this away. Follow? Correct? N divided by n, I get 1. So I get n minus 1 over n plus 1 times un minus 2. So now, can we look at what is un minus 2? Un minus 2, if I use this formula, I replace n with n minus 3. Yes, I replace this with n minus 3, I will get n minus 2 over n minus 1 un minus 3. So that explains this expression here. So I replace and replace and replace until I see some kind of pattern. Follow so far? So I can now see that this n plus minus 1 n minus 1 also goes. And on and on and on. Now, let's focus on this part. Let's focus here now. Okay, let's focus here. eventually, I want to express un in terms of n, which is an explicit formula, right? I want an explicit formula. The un minus 3 is not good enough for me. I don't like un minus 3. I need to go down and down and down and down all the way to u1 because I know what is u1. u1 is a number that I know. Not good enough to stay at un minus 3. So let's see the pattern. Now, if it is un minus 3, then the numerator is n minus 2, denominator is n plus 1. Now, can I make this here, sorry, what value, or rather what do I substitute into here, 3, such that I will get u1? I say again. Now, you see, there's always a pattern. Let's compare these two. Okay, maybe I erase all these first. Yeah, like that. Let's look here and look here. These two look similar. If this is a 2, minus 2, this is a minus 1. Then it's a plus 1. If this is a minus 3, it will be a minus 2, it will be a plus 1. So this plus 1 always stays there, regardless. So I always have an n plus 1 in the denominator, regardless. Follow so far? See pattern. Now, if this is an n minus 3, this must be a n minus 2. Correct? So, logically speaking, if this is a n minus 1, I change the 3 to n minus 1, I will get a u1. Follow so far? If I change if this is n minus 1, this should be n minus 2. Okay, never mind. I use another way to explain. If you understand this well and good, then we can answer, okay? I use another way to explain. How do we get from here to here? It's a little bit more direct. First of all, we observe the denominator must always be n plus 1. So n plus 1 will always be there. I know that eventually I must go down to u1. If I change the n, this n minus 2 is one larger than n minus 3. Correct? If this is 10, this must be 11. Correct? If this is 20, this must be 21. Because of this pattern. N minus 2, n minus 1. Follow so far? So if this is 1, then this must be 2. Done. As easy as that. Actually, if you don't like this line, you can actually cancel away this. If you can see this from this line to this line directly, actually I'm fine. You get what I'm trying to say? Abstract or easy? I say again, maybe I zoom in a little bit more. Spot pattern, n plus 1, the denominator must be n plus 1. I want this to be u1 because I know what is u1. This is a general formula. Numerator is always one larger than this subscript. If I want this subscript to be 1, the numerator therefore must be 2. Done. Comprehensive enough. So what is u1? u1 is 3. And then I get my formula. Okay? This is how we find an explicit formula. There is only one practice. There is only one such example in the entire set of notes. Okay, never mind. I give you about 2 minutes, talk to your friend, okay, about this.